I'm looking forward to about a 30-minute presentation here where we're going to talk about some high-level aspects of electric vehicle charging, in particular the requirements for the power electronics inside those systems. And hopefully we'll stir some interest and get some great questions from you all at the end. Okay, so a brief overview of what I'm going to talk about. This is really going to be quite high-level stuff. Firstly, I'd like to talk about the two main types of chargers that you'll see in the field when you're charging your electric vehicle, just to differentiate between the architectures of those. I'll then move on to have a little look at some of the typical charger requirements and the sort of aspects that we like to design into these chargers to make sure they perform well. And we'll briefly discuss then the hardware system architecture that is suitable for this sort of an application. And we'll dive into some of the details of the power conversion stages. So we will get into some details of topologies and power flow and things like that. And also to give you an idea of the typical sort of performance levels that we could start to be able to achieve using modern approaches to power conversion. I'll finish off at the end with some conclusions and maybe a few ideas about what the future might hold for this space and how technology might progress as we move forward through e-mobility and electrification. So firstly, there are two main types of charger that you might hear talked about in the field: AC chargers and DC chargers. And this is really just to give you a bit of a feel on the difference between the two. So if I start with AC chargers, first of all, an AC charger, really the charging station that you see by the side of the road with an AC charger, really what its role is to provide AC power to the car and provide all the control, diagnostics and metering function. And actually inside the car is a box of power electronics, which then converts the AC power from the AC station and turns it into DC, which is required to charge the battery. And that tends to be roughly what's inside these particular AC stations. There's no real power conversion or heavy power electronics inside those stations. In terms of power capability, if it's a single phase system in the UK, you can typically get up to about 7 kilowatts on single phase, which is 32 amps on that phase. With three phase, you can take that up to about 22 kilowatts, but it really depends on the capability of the onboard charger on the car. That will determine ultimately the power that is drawn from the AC supply. And to put it in context, if you plug into a 7 kilowatt charger, then you'll put about maybe 25 miles of range onto your car for every hour that you're charging. And if it's 22 kilowatts, it's about 75 miles of range per hour of charging. So that's fairly low charge rates, low to medium charge rates. If you want to charge your battery faster than that, the box of electronics that is sitting on the car, the onboard charger here, it becomes too big and expensive for you to have on your car. You can't just have an asset that's a high power converter sat on your car not doing anything most of the time. So in those scenarios, what happens is the charging station itself now contains a power converter block. In fact, effectively, it's a bit like the onboard charger on the car has shifted out and is now sitting in the external station. The power levels you can get really are then determined by the availability of AC power, but more importantly, the power capability of the battery, or the ability of the battery to absorb energy and the rate at which you can charge. So you can see here, it's a very subtle difference. It's just a position of where that box of power electronics is determines whether it's an AC charger or a DC charger. Okay, so I'm going to talk mainly about that box of electronics. So whether it's an AC charger, that box of electronics sits on the car. If it's a DC charger, it's in the charging station. Both of them are doing roughly the same thing. They're converting a power source, normally three-phase or single-phase AC, and they're turning it into a high-voltage DC supply to charge a battery. And there are certain requirements you would like to have that system meet. Obviously, high efficiency is very important. That's really because you want to minimize energy waste, and for a number of reasons. Obviously, energy costs money and it generates carbon emissions. So you want to minimize the wasteful use of energy. So high efficiency is good for that. You also want to maximize efficiency because any power inefficiency in the system is lost as heat, and it's quite difficult to manage heat generation inside a piece of electronics. So you want to make it efficient to keep it nice and cool. That also helps with reliability. If you can keep your power electronics cool, it tends to make it more reliable. So the first thing is really high efficiency. The second thing is you want to have a very wide output operating range. And in a few slides' time, I'll discuss what I mean by that. But essentially, what it means is we want that DC or that box of power electronics to be able to charge all sorts of different batteries, charge as many different types of vehicles as possible, so that you can, any vehicle could pull up and charge from it is really the ideal case. AC or DC input, well, at the moment, nearly everything is AC input because most charging stations are fed from the AC grid, whether it's three-phase or single-phase. In the future, I won't be talking about this today, but in the future, you might start to see scenarios where systems become native DC input to allow for situations like local battery energy storage and local micro generation. Those sorts of energy storage schemes are natively DC. So maybe in the future, when we have local energy storage on the grid, that's when we might start looking at DC input stations. But the rest of this presentation, I'm talking about AC input. AC harmonic correction, some of you may have come across this before, and I'll come onto this later because it's a really essential part of an AC fed system. Galvanic isolation. So if you're feeding power to your car battery from the grid, you don't want a direct electrical connection between the grid and your car because of all sorts of reasons, but mainly it's safety, EMI, and regulatory requirements that prevent you from doing that. So we need to have an isolation barrier within our system as well. And one final one, or requirement for thought here is, well, do we need bidirectional capability? Most systems at the moment are unidirectional, and they take energy from the primary energy source, so the grid, and they charge the battery. If you can make that energy or that power converter in the middle of that process bidirectional, then you can start doing some really interesting stuff with vehicle to grid. If you imagine when you have mass adoption of electric vehicles, all of these cars are essentially mobile batteries that you could use for peak load mitigation on the grid, local backup, all sorts of stuff. So bidirectional is quite an interesting one to watch. Okay, so moving now onto system level architecture and basic requirements. This is about the most simple way I could draw an AC input charger, just incorporating some of the aspects I've spoken about before. So it's a black box, and if only life were this simple. The black box at the moment, we've got three-phase AC coming in on the input, so line 1, line 2, line 3. You don't necessarily need a neutral, but some systems do use them, some don't, and we have a safety earth, so a typical 5-wire AC feed here. And on the output side, we have a galvanically isolated high voltage DC supply which feeds the battery. Now, the interesting thing, charging a battery, you need a current. It needs to be a current source. So this high voltage DC output is not a fixed voltage of say 400 or 500 volts. It's actually a fixed current, and the control of the battery charger forces a fixed current into the battery. But it's not the battery charger which determines the current. It's actually the battery in the car, or the battery management system in the car, that tells the charger what current it wants. Because if you imagine a situation where you've been driving down the motorway, for example, your battery is very hot, well, the battery management system in the car may actually require a lower charge current to protect the battery from overheating. So really the intelligent part of the control is managed by the battery management system, which communicates with the battery charger to tell the battery charger what current to deliver. And it does that via the charge cable. There's various different schemes, J1772 or 15118 are typical communication schemes. And they're just a communication between the battery charger and the car, but really the car is in charge of what power it wants to receive. Okay, so we're diving now a little bit more into some of the architecture side of what sits further inside this battery charger. Now, there's all sorts of different ways you can physically implement the function, the black box function I spoke about earlier. Some of the most common ways of doing this split that power conversion process into two main parts. You have two power converters to do that. And that's what I'm going to talk about today. The first power converter is called a rectifier, or an active rectifier. And what that does is it turns the three-phase AC input into a high voltage intermediate DC link. And it needs to do that in a certain particular way, which I'll describe on the next slide. But essentially, we're chopping up and turning that AC into a high voltage DC link. That high voltage DC link is then fed to a second stage converter. Now, the rectifier itself doesn't provide isolation or control over current or anything like that. So this provides a raw DC supply to this second stage converter. And that second stage converter is an isolated DC to DC converter, which takes the energy provided by the active rectifier, controls and manipulates it to provide a controlled output current, and provides an isolation barrier. Now, it sounds like a simple thing to do. It's actually quite complicated to make that work well, but that's essentially at a high level what's happening inside this particular battery charger. All of these are controlled and manipulated and by an intelligent digital system, which allows all the sort of comms to the car and the external world and diagnostics and stuff like that. But at an architecture level, that's roughly what you're going to see inside one of these high-power DC chargers. Okay, so I'm going to talk a little bit now about that first stage, the rectification stage, where we're turning AC into high voltage DC. And the best way I felt to describe this is how not to do it. So we have a high power DC supply in our lab, which has standard rectification on the input. So there's nothing clever about the rectification of that. It's actually, if you were to open up that lab power supply, on the front end, you would see this three-phase bridge rectifier, whereby you feed in the three AC signals, and that generates a high voltage DC link. And that's a very traditional way of doing it. The trouble you get with this approach is that this is actually a plot from our three-phase power analyzer of that power supply driving about 2.6 kilowatts of useful power. And you can see here that the yellow, red, and magenta colored plots are the phase voltages, so line 1, line 2, and line 3. And then overlaid on top of that, you can see the phase currents for the respective phases. And you can see here, the phase currents are about as far from sinusoidal as you could possibly be. They're pretty ugly. And the effect that has is it causes additional stress on the AC feed powering that system. And that is reflected in what's known as the power factor, which I'm sure many of you have come across. So in this system here, when I was running 2.6 kilowatts to grab this plot for the presentation, the power factor I noticed on the meter was about 0.5. And we were pulling about 7.3 amps RMS per phase. Now, if we try and normalize that, what that really means is that for a three-phase system with 1 amp RMS phase current per phase, we get about 360 watts of useful DC link power. So sounds okay, but the important point now is if we compare that to an active rectifier. Now, at a first glance, the active rectifier looks quite similar. You can still see that there's 6 of these diodes here, but now with each of those diodes, we've put a power semiconductor switch, and in this case here, I've drawn it as an IGBT. It could actually be a MOSFET or a silicon carbide MOSFET. And we've got 3 inductors on the input. Now that turns this power stage essentially into a form of a boost converter on a per phase basis. And the great thing about this particular topology is we can now control and manipulate the voltage, the effective line frequency voltage at each end of the inductor with an amplitude and a phase relationship to the input to allow us to control power factor to whatever we want it to be. And in most cases, we want unity power factor. And there's clever ways you go about controlling this, but essentially what we're doing is we're using high frequency switching of the order of 10, 20, or 30 kilohertz on these devices, or even higher, to control and manipulate the current being drawn on each phase to make it match the voltages. So on the plot here, you can see yellow is the phase 1 voltage and green is the phase 1 current. And you can see they're both roughly sinusoidal and they're both in phase. So what that manifests itself, in this case, this was an old plot where we were pulling about 12.8 kilowatts through this converter. The power meter gives us a power factor of 0.99. And what that means is nearly 100% of the current that we're pulling is at the fundamental frequency and in phase with the fundamental voltage, which is about the best way you can treat the grid feeding the system. If we want to normalize that, because this is a higher power scenario, of course, if we want to normalize that and compare to the standard three-phase rectification, you can see now in this case, for every 1 amp of RMS phase current on the three-phase system that we have, that now delivers 720 watts of useful DC link power, which gives you an idea. This isn't, we're not burning more power in the three-phase rectifier. They're both highly efficient conversion systems. But what we're doing with the active rectification is we're minimizing the current draw on the three-phase feed coming in for a given output power in a much better manner and a nicer manner than we can achieve with standard rectification. So active rectification is by far what you need to be doing, and actually it's mandated by regulation that you have to do this sort of stuff. Otherwise, the grid would suffer awful problems as power levels go up. There's an additional really interesting factor that comes into it with active rectification. If you look back at the standard three-phase rectification, you can see here that because of the way the diodes are polarized here, there's no way you can get any power flow from this DC link back out to the lines of the phase supply. So essentially, the standard three-phase rectifier can only ever support unidirectional power flow from the three-phase AC to the DC. However, with the active rectification here, you can see we can actually conduct current back through the active devices here, which gives us an ability to have a bidirectional converter. We, a couple of years ago, experimented with various different control schemes for building one of these active rectifiers on a rapid prototyping system we've developed called Hardware Stack. And this is just a plot, an example of one of those tests we did a few years ago, whereby we've switched from exporting current to importing current very, very quickly using this active rectifier. You can, in this particular measurement case, we've gone from a 5.2 kilowatt three-phase export to a 5.2 kilowatt three-phase import, roughly halfway through this transition. The blue line is the phase voltage. We're only showing one of the phases here, but there are 3 in total. On this one phase we're looking at, you can see the blue line is the phase voltage, green line is the phase current, and at the point of transition, you get 180 degrees phase shift in the phase current. The brown line here is the calculated phase power, which is just the product of phase current and phase voltage. So you can see here, we're in both cases, we're operating with near unity power factor, whether we're importing or exporting. However, look how quickly you can transition between those two. When you have an active power electronic system, things can be controlled very quickly. So we've transitioned from import of 5.2 kilowatts to export of 5.2 kilowatts in about 1 millisecond. And the efficiency of that particular conversion process is about 99%. So it's a fantastic way to manage that interface between the worlds of AC and DC needed to charge batteries. So that's it for the active rectifier front end. Now, the second stage converter, again, there are lots of different ways you can go about implementing that. You need to have isolation, so you need some form of transformer-based topology. And there's an example I've used here, a company called Cree, who manufacture all sorts of high-performance power semiconductors. This is an example taken from their website. You can download this as well if you want to. It's a 20 kilowatt LLC converter, which is a resonant converter system here. The input of this system is essentially the high voltage DC link from the output of the rectifier stage we were just talking about. And then we control these particular 4 bridge devices. And in this particular topology, we control it by changing the operating frequency to send power through the transformers and out through the output rectifiers and output to the battery. The good thing about an LLC topology is it provides 0 voltage switching on the primary bridge devices. So these 4 devices on the primary form a bridge circuit. And this particular topology makes sure that they only turn on when they've got 0 voltage across them, which gives you very high operating efficiency in that particular system. These particular devices are also Silicon Carbide devices, which are a type of wide bandgap technology which moves you closer to the ideal switch. With all of these power electronic systems, you're you're controlling and manipulating power flow by turning power devices on and off at very high frequency. And you want those power devices to behave as close as possible as an ideal switch and move between those two states with minimum loss. And these silicon carbide devices are about the best way you can do that at the moment at the voltage levels we need here. This particular topology uses a variable operating frequency, and in this case, it's about 110 to 350 kilohertz. The good thing about going to higher operating frequency using these silicon carbide devices is it allows you to minimize the size of the transformer and inductor elements here, the magnetic components. And a good comparison, if you were to try and transfer 20 kilowatts of power using a normal 50 hertz line frequency transformer, you just wouldn't be able to pick it up. And these are so much smaller than line frequency operation. However, you have to be careful how you design them, and you need to understand the loss mechanisms that those devices will be subjected to, and I'll talk about that in a little bit as well. The efficiency measurements, these are straight from the data sheet for this part, are fantastic. I mean, this topology is one of the best out there for high performance. However, you've got to always be a bit careful on how you interpret these efficiency points, because there's always a certain amount of marketing involved. So these efficiency points here are corresponding to the point of operation of this converter where it's performing at its absolute best, which is what many people do, but you need to make sure that under real operating conditions, you understand how it operates as well. And I'll talk about that in the next few slides. Okay, so we've covered the two main topologies. In terms of the operating range of this battery charger, if you look at the plot on the left-hand side here, normally you have an operating window for your battery charger, whereby you have a certain maximum voltage capability, a certain maximum power capability, and a certain maximum current capability. You can't operate beyond these ranges, but if you operate at high voltage than that, you might damage some of the semiconductors. If you try and operate at a higher power level than Pmax, well, your system might overheat, and similarly, you could damage the semiconductors and other parts if you try and put more than Imax through them. So you design your converter with these upper limits, but in practice, remember from earlier, it's actually the battery management system in the car which is dictating the amount of or the charging current and how the system is behaving. And it's fairly unlikely you're going to be sitting at these optimum points on this maximum curve for very long. The middle plot here shows a typical charging scheme for a lithium-ion battery cell. An electric vehicle battery comprises a lot of these cells put together. But you can see here in this example scheme, for the first hour of charging, we're delivering a constant current. The terminal voltage on the battery starts to increase over that time, and when the battery management system recognizes you've got to a certain cell voltage, it will then tell the charger to start reducing the current level accordingly. So you end up with this trajectory here in this example here, this is a 4-hour charge time. It's really just to show that there are different modes of operation depending on the cell chemistry and the particular battery management system of the manufacturer of the vehicle or the battery pack. The actual operating point, as I said, is determined by that battery management system. And most of the charge duration is spent at points other than these ideal ones where the maximum efficiency curves. So maximum efficiency occurs. So the important thing is to understand not just how your converter is performing at these peak points, but also what happens during a normal charging trajectory of a real battery. If I click here, you should hopefully see in the right-hand figure here a video of a simulated charging profile of a typical battery pack. You can see now we're charging over a period of, in this case, 4 hours, but obviously I've sped it up quite a lot. At the start of the charging cycle, we've operated for the first 60 minutes at full rated current, and that operates us right on the peak maximum part of the curve here of our converter. So that's great, that's really high efficiency. After the 1 hour time, the battery, in this case, I've approximated it as a straight line, but the battery management system starts to reduce the current demand, and the cell voltage is fairly constant. So after 1 hour, we start to traverse this trajectory through the VI map of our battery charger. And we actually spend quite a lot of our time away from this peak power point. And it really depends again on what the algorithms are used in the BMS system. If you look at the battery energy over time, obviously in the first hour we've delivered about 60 kilowatt hours because we've had, we've had delivered 10 kilowatt hours because we've had 10 kilowatts for 1 hour. But that's only about a third of the total energy delivered to the battery. So a large part of the energy delivered to the battery occurs away from that idealized operating point. So we need to understand how our converter is performing in these other regions, not just out here. So hopefully that makes sense. I'm happy to come back and answer questions on that at the end if anybody's got questions on that. So how do we go about understanding the performance of those different operating points? There's all sorts of ways you can go about doing this. We've come up with some analytical ways which use something called a first harmonic approximation, which is it's a way of modeling this particular LLC converter under all of the sort of operating conditions you might find your battery charger is being exposed to. And what it allows you to do is to gather data from all the different operating points and then start plotting out stress levels. And from that, you can work out loss. And from loss, you can work out efficiency of the system. And this first plot here shows you a typical operating efficiency map of this LLC converter that we were talking about earlier. So you can see here, the most efficient region of operation is this slightly orangey colored region where probably the most efficient point is the 20 amps, 500 volt point. As we move further away from this optimum region, efficiency starts to degrade. And the worst case for efficiency is either maximum current and minimum output voltage, or minimum current and maximum output voltage. So it's these extremes of operation that not just the LLC, but all sorts of converters tend to struggle with those extreme cases. This particular efficiency prediction is slightly optimistic, by the way, as well. We found that our loss models for the magnetics were not as accurate as we hoped. So these are slightly optimistic. Now then, with the same analysis, you can then drill down into looking at the breakdown of losses through the system under all of those operating points. So if we look at the total loss, you can see we've got about 140 watts of loss, worst case, up at this operating part, or this part of the operating window. The transformer loss is worse at that point, but it's only about 20 watts of that particular balance. It's a small fraction of the overall loss. The inductor loss, there's a resonant inductor in the LLC, that's about 12 watts. But look how much loss we've got in the semiconductors. The majority of the loss in the system at these operating points is actually due to the power semiconductors. And it's not because they're bad, it's just because of the way this system works. The important thing here is we now know where the dominant loss mechanisms are. So we know how or where to spend time and money to try and improve the system. We may as well do it on the semiconductors. If we then break the semiconductor loss down even further, we can start to see that it's dominated by the output rectifiers. So we've got about 20 watts of the silicon carbide FETs, but you've got about 100 watts on the output rectifiers. So that's where the majority of the power loss is going. So this sort of analysis gives us a great way to understand how to improve our system performance. So to briefly summarize, the key aspects of the second stage DC to DC converter, and actually the active rectifier, I suppose, as well, is that we need to be able to understand and model all the dominant loss mechanisms over that full range of VI combinations that a battery charger might be exposed to for an electric vehicle. And the more we know about that, the better job we can do of optimizing energy delivery to the battery. One key thing we found here is it's really important for the high frequency magnetics, these magnetics running at hundreds of kilohertz, is you have to spend a lot of effort to make sure you can design those yourself. If you more often than not, the sort of loss mechanisms you've got there are fairly complex. Things like fringing fields, for example, and this is a finite element model of an inductor we built for this application. These fringing fields around the air gaps, they impose additional losses in the windings of the transformer. We get a very non-linear increase in hysteresis and eddy current loss in the transformer ferrite as we go up in frequency. We get problems with skin effects and proximity effects in the winding. So generally things get a lot harder for magnetics and capacitors as well. But magnetics really, to get those to work well at high frequency, you've got to be on top of all of these loss mechanisms and understand how to manipulate and control them. Silicon carbide devices are fantastic. You have to be a little bit careful with the gate drive voltages. They're not as robust yet as silicon devices, although they are in mainstream production and they work fine. You've just got to be a bit more careful with them. Operation at high frequency, so hundreds of kilohertz and tens of kilowatts, that really does require careful layout and system design to avoid electromagnetic interference, which is always a problem for any switching system. So we have to be very careful on the EMI there. A great way for all of these things to de-risk early is to do rapid prototyping, and that's what we do to prove out new converters. You need to try and get something running on the bench as early as you can. Then you understand what the major problems are, and you can start focusing on the key issues. So early prototyping is a fantastic way to de-risk projects. So I think we're pretty much just coming through to conclusions now. Hopefully the message I've been able to communicate today is how important power electronics is, forming the core of the future low carbon economy, especially e-mobility. The ability to control and manipulate electrical energy and in such a granular and fine fashion that power electronics can do. This is really key to the future of e-mobility. Anything to where we're transferring a lot of energy around the place, high efficiency is absolutely essential for the success of these technologies. We just don't want to be burning and wasting energy as heat. Wide bandgap power semiconductors are a great way to meet some of the efficiency targets, and advanced magnetics can start to achieve some really high performance levels, but you've got to really control their design very carefully. In the future, well, it's difficult to predict really. There's all sorts of things that could happen. Some of the things I think might be interesting is for very high power chargers, for maybe buses or even bigger vehicles. Maybe some of the power electronics starts moving up to the medium voltage level. So all the stuff I've talked about so far is operating off 415 volt RMS three-phase. Maybe we need to start stepping the voltage level up to higher levels to increase the performance even further. So that's a food for thought for you today. Bidirectional capability is a particular interest of mine. I don't know if the commercial aspects of that have been proven out yet, but I think longer term it'll be an essential part of the whole energy ecosystem, not just e-mobility, but grid support, grid storage, and microgeneration. Okay, I think we're just about done. Thank you for your patience. I'd be happy to take any questions.